ball bearing that was inside a journal bearing, right? Okay, so everybody knows what the connections are, right? What's a synonym for connections? Supports. Okay? What does it mean, Lonnie, by reactions at supports? Oh, really?
Yeah.
Oh, good. I didn't know it.
It means that it resists the force at that point up to a point where it
Right.
can.
Right. So, Lucas, for a, what is this? Ball and socket joint. I'm connecting my arm to my body. There's two pieces that are being connected. What can it resist? Can I spin? Can I spin?
So it can be forces.
Right. In X, Y, and Z. In all three. So the reactions at a support of a ball and socket joint are three. Force in the X, force in the Y, force in the Z, right? But a 3D, DJ, a 3D connection has the possibility of resisting how many?
6.
All six. 3 forces and 3 moments, right? Everybody has that? On a 3D connection, there's a possibility of it resisting 6, having 6 reactions at a support. 3 forces, 3 moments. Kyle, on a 2D problem, what's the maximum amount of reactions at a support?
3.
3, and what are they?
2 forces. And
2 forces, a force in the X, a force in the Y, and a moment about
Z.
Z. David, so what is a reaction at a support? Okay, Daniel, what's a reaction at a support?
Something that you can't move to. Or,
It's not free to move,
Right.
it resists, right? Okay? Okay, so we went through all those, and now what we're going to start to do is draw free body diagrams. So we're going to do the first one together. So the ones we're going to work on are the ones that I circled up here. So let's look at the thing here. Draw a complete free body diagram so the body is specified in the following problems. Neglect the weight of the member except where the problem statement indicates that the weight of the member is to be considered. What does it mean by that? Look at number 1. See how there's a little G there? What is that? What do you think that G means?
Gravity.
Gravity, the center of gravity. So we're going to draw the weight for that one because it's showing us the position. On other ones, it doesn't show us, so we're not using the weight. Assume that all surfaces are smooth unless otherwise indicated. So what do they want us to do for number 3, 5? They want us to draw a free body diagram of the curved bar. So I'm drawing the curved bar. This is point B. This is point C. And this is point B. So let's start with the forces. So Eugene, what forces should I show on that free body diagram? What is that bar being subjected to?
Moment.
No. You're right. It's no. What are some things that are shown here that we need to indicate? There are 2 things on here that we already know about, and it has nothing to do with connection. So what are they? Right, force P. I need to draw force P on it. And what's the other one, Eugene? Okay, there's something there. What is that thing going from A to B? It's a cable, right? So you got to draw tension. So which way does draw? If I'm drawing a free body diagram of BCD, which way do I draw it? Down, away. We always draw tension away. Draw tension. This is 30. That's 30. So far we drew 2 things that we already know how to draw. We already know how to draw tension, and we already know how to draw some kind of external forces. So Isak, there's something else I have to do now. What is going on at C?
There's
What kind of,
moment about C, or
tell me what kind of connection it is first. Can you tell by the picture? You have to
Is
get
it a
comfortable.
pin?
It's a pin. And what does a pin resist? What are the reactions at a
resist the
pin?
forces.
Forces. So a force in the X and a force in the Y. That's it, we're done. So I think you guys are getting a little bit more complicated, like, oh, there's a moment here. Well, yeah, there's probably a moment created by P and by the tension, but the reactions at C are gonna resist that spin, right? Okay, so what did I do? Everybody take a deep breath. They asked us to draw the curved bar. We drew it. We look at the bar. We see, oh, there's a P on it. We draw the P. Oh, there's a tension on it. We draw the tension. And then, in addition, when we take this curved bar away, we just removed it from something, right? And whenever we remove it from something, just like, remember the problem a long time ago where we had two cylinders touch each other. When I removed the cylinders, what did I have to put in there? Normals, right? When I want to analyze this and it's on the surface, when I draw its free body diagram, what do I have to put in there now? The normal, right? The normal going up and its weight. So once I take this curved bar away from this little piece right here, I have to account for that. So the first thing I need to do is look at it and say, what connection is that? And Aesop realized it was a pin. So you got to be comfortable with the pictures. And we know that the reactions at a pin are a force in the x and a force in the y. That's all we're doing on this exercise is to draw the free body diagrams. If we went back and continued the problem, what would we do next? Sam, what would you do next? Let's assume that P and T are given. So if P and T were given and it was a full statics problem, what would we do? If we were given the value of P and we were given the value of T and it was a full statics problem, what would we want to find?
Probably Fy and Fx.
Yeah, we want to calculate what Fy and Fx are, right? And how would we do that, Jose? How would we be able to calculate Fx and Fy if we knew P and T?
Well, I'd probably start by breaking T into its X and Y components.
Okay. And then what would you do?
And then I'd find, and then I set both the sum of the components to be 0 and solve for X.
The sum of the forces in the x equal to 0 and the sum of the forces in the y to be 0.
Yeah.
Right. So if we are given P and T, and we don't know Fx and Fy, that would be two unknowns. And two unknowns, we need two equations, and we're going to use the equilibrium equations.
Would we still need to draw our x's or showing the
Yeah,
Fy?
you still have to show the axes.
Okay.
Is that what you're asking?
Yeah.
So let's just draw it up here to the side.
So having
Whenever it's asking us to draw free body diagrams, we always have to draw up the axes, always. Because you're setting which direction you want your axis to be. Santiago?
You're not drawing the moment in Z, but is that because it doesn't resist the moment?
Right, because a pin allows it to spin, right? A pin, when a pin connects two things, I don't have the toys now, they're up in the STEM center, but when I have two things connected by a pin, they can spin relative to each other. So they're not going to resist each other, right? So in that case, it's not going to break that way. In essence, Terlin, when we calculate Fx and Fy, we're able to find out how strong a pin we need, right? Because we're calculating P and the tension are causing forces on C, right? And if those forces are great, it's going to break the pin. So as engineers, it's very important that we find these two so we know how strong that pin has to be to withstand these two. Okay? Let's talk about that since the engineering part's the most important, right? Let's say we calculate Fx to be 100 pounds, and let's say we calculate Fy to be 100 pounds. Terlin, how much do I need to design? What force do I need to design this pin for?
Shear force?
Yeah, it is a shear force. That's good. I need to want to know that. What's the number? That's great. Because some of you haven't taken material, so you might not know it's a shear. But that's exactly what it is. numerically, my question, I meant it to be a numeric, what's a numerical value? Everybody think about that. Does it need to withstand 100 pounds, or does it need to withstand more than 100 pounds? Carolyn,
That needs to be the magnitude of the force.
it needs to be the magnitude, it needs to be the result. And what's this result? Isn't it like 141.1 or something? I think that's what it is.
Did you just do that in your head, Joanne?
Yeah, but no, I didn't do the math in my head. Just- I've used these numbers before, so it's just, no, I can't do that. I'm not- So it needs to be able to withstand 100, does everybody understand that? If you pick a pin that holds 100 pounds, you blew it. Because this pin really has to hold this amount, right? And then, in engineering, Jason, what do we even want to do more? Do we want to design it for 141? What do we want to do? We want to add a factor of safety. So let's say the factor of safety is 3. Jason, take a stab at this. If the factor of safety is 3, what do we want to design this pin for? 3 times it. So we would want to design it for 1 bat times 3. Okay? But in statics, we don't talk about factors of safety. I mean, well, we can talk about it, but we're not calculating factors of safety at all. If I were to ask what the pin has to withstand, it would have to withstand that result. Does everybody get that? Okay. Okay, so what are we doing? We are doing what we've done before. We are taking a body and we're drawing all the forces and moments on that body. You've already done it, okay? So it's really nothing. The only thing new that we're doing is now we're recognizing what connection it is and what we have to draw. And what do we draw at? Santiago. Wait, did we go? Yeah. Where did I start? Oh, I started with Jack, so Santiago. What are we drawing? On C, I drew Fx and Fy. Why did I draw Fx and Fy?
Because those are the moments that the forces that are resisted.
Right, those are the reactions at the supports. Okay, so we're up to the next one now. So now what I want you to do, the next one we're going to do is 8. So I want you to work with the person next to you and draw the free body diagram of the beam. Okay, you should be able to do this in less than a minute. The beam. Draw the beam. You can just draw a line.
You just want us to draw it or
Draw the free body diagram of the beam.